All right. I think we're gonna go ahead and get started with the chassis portion of the presentation with Branson Leonard, our chassis lead.
Good afternoon. Hope everybody enjoyed lunch. My name is Branson Leonard. I'm the lead of the chassis side of the team. And on the chassis side of the team, we have brakes, frame, suspension components, kinematics, aerodynamics, body, ergo, and drivetrain. So my name's Branson, of course, I'm doing the brake system. All right, so for this year, we wanted to do a system that weighs less than 12 pounds. Last year, our system weighed 13.1. But with the changes we're making in the system between the pedals and the rotors, we want to weigh less than 12 pounds. And then the other change I want to make for a design goal is to have the braking bias set for your average dynamic load during weight transfer during competition. And with this change, the changes that are going to help to meet the goals is different size rotors between the front and the back. The front is a 7.6 inch diameter rotor and the rear is a 7-inch rotor. The front calipers are changing to a new style. I'll get to that in the next slide. And then the master cylinder sizes. The front master cylinder, we can't change the size anymore. We've run the smallest there is. And for the rear master cylinder, we are using a smaller size than last year. And then the gas pedal redesign, I'll get to that in a couple slides. All right, so this is the front caliper. This is an ISR caliper offered by ISR. It's a 4-piston caliper, aluminum. So the reason we're going to this caliper, it allows for more clamping force on the rotors. It weighs the same thing as a caliper we used last year, which is another aluminum caliper offered by Willwood. And this caliper, it's radially mounted to the upright. And so with this radial mounting, it's stronger on the upright. It helps increase the factor of safety. And so this is the gas pedal redesign. So right now, this is those are the 2 tabs at the bottom that mount it to the chassis. You have a metal machine insert at the bottom that holds, that's a carbon tube. And at the top is a 3D printed part. That's going to be the pedal face. And it's going to be mounted to the carbon tube at the top. And that is a rod end for the throttle body wire to connect to the gas pedal. And in the middle, I don't have the models for them, but we use RC shocks and springs as our throttle return springs on the pedal. And so the big thing about this year was trying to make sure that I could still reduce weight while making some design changes. And so one thing I didn't do in the past was changing the pedal system. So that's what I worked on this year, was changing the gas pedal. The weight of this pedal in SolidWorks, I think it was 1/4 pound, and compared to last year, which was, I think, a little under a single pound. So other than that, not much has changed. The rotors are slightly different diameters. Last year we ran a 7 3/4 inch diameter, but this year is going to be a 7.6 inch. But that's just to help with the bias for front and rear turn braking. Are there any questions? Go ahead, John.
Can you talk a little bit on the brake failure we had in Michigan?
Yes, of course. I'm sure Shogo would like to hear about that too. So during Michigan this past year, part of my system that failed was the tabs that mount the master cylinders in the brake pedal to the front, two bracings in the front, the bars in the chassis. During brake tech, so just an explanation of what brake tech is for people that don't know. Brake tech is I think it's like 60 feet to get as fast as possible, and then you have to slam the brakes and you have to lock all 4 wheels at the same time and bring the car to a stop without any failures on the car. Without killing the car, like making the motor stop, and then continue off track. But so during brake tech, we actually had our tabs that mount the master cylinders and the pedal to the chassis. They buckled, and that was due to a design error on my half. I changed the design of the tabs and I forgot to redesign or FEA the tabs. And I went back and I re-FEA'd it, and it showed an FEA of 0.97. So it was obvious that it was gonna fail, but I changed the thicknesses. It was a 16th inch of steel, and I changed it to an 1/8, and I redid the FBA, and it was, I believe, 1.36. So,
That's a safety factor.
yes, factory safety, correct.
Where do you get all the loads that you test your pedals for?
So-
So just looking at that pedal, I mean, you're not always very friendly to the car when you're driving.
Yes,
Racing
correct. Well, this
cars.
is the gas pedal. It doesn't see as part of a braking force as the brake pedal. The difference between the gas pedal and the brake pedal. So what stops this from fully traveling is the bulkhead. So the loading that this sees compared to the brake pedal, I think the max that this sees compared to the brake pedal is like, let's say 100 pounds compared to the brake pedal, which is you designed for in the rules for, I think it's 250 pounds into the brake pedal, of course. I don't have any calculations for this, but in my design, the weakest point on the whole system is the plastic piece at the top. I don't have the factor of safety for this off the top of my head, but because that is ABS, or not ABS, I think that's gonna be nylon. There's a company I found that has a little stronger than ABS, but for just the loading of this, the only thing that stops it from moving is the bulkhead. So all your loading is done at the top, and it's a carbon tube. This is the same carbon tube we used for the steering column as last year in 18. So the torsional stiffness is fine, but
So do you,
okay. I can point. I'll give you show.
do you have you made estimates of the loads that the pedal may experience, not just during normal conditions, but maybe some,
You talking about for gas pedal or the brake pedal?
I'm talking about,
This is the gas pedal. Correct.
but it doesn't matter which
Yeah.
one it is, but you should do the analysis and you should have an estimate of the loads, even if it's a mistake, if a load is applied by mistake,
Mhm.
right? You don't want to break this, right?
Yeah.
Whether it's on competition or off. And when you use 3D printed parts, you need to know what the properties are,
Mhm.
because you can't use bulk material properties. When you 3D print, you don't get the same strength. So that's something to consider.
Okay.
You said the 3D printed part on this is what type of technology are you going to use to print it?
I actually talked with one of our alumni, Cody, a lot, and I work with him, and he showed me this company that for the cost analysis versus like the actual part itself, the strength. I don't know what the properties are, but he's tested between this and ABS plastic and the stuff that that company uses. It's just like I haven't done any testing on it yet because I haven't ordered any parts for it, but it is obvious that it's stronger than the stuff we use because it does not flex under just like hand loads compared to the stuff that we use for ABS printing.
So that's seat of the pants engineering.
Yes. I
And
know.
so yeah, it could, exactly. So you need to actually
Correct.
get all the information,
Mhm.
quantitative terms, and do not just believe what you're
Mhm.
being told, especially if it's from the manufacturer.
Correct. Yes.
Right?
Mhm.
So make sure you do due diligence, because again, it would be very disappointing if
Failure
you're
happened.
compromised because of a failure that
Correct.
could have prevented.
Yep, I just got the contact information for the company, so I was planning on talking to them in the following weeks to get information about that.
And also consider using, a 3D printer that produces composite, like a carbon fiber, chopped carbon fiber,
Okay.
that exists here in your backyard.
Okay.
Uh,
Yeah, I just know it's slightly expensive to do that, and the
Yeah,
cost.
cost is a factor, but cost is not the only factor.
Yeah, correct.
Maybe keep a metal spare in the toolbox as well.
Well,
For when it
so that's
does.
the other thing, redundancy.
Yeah.
To follow up on very similar problem actually. If I understand correctly, so the work part is carbon fiber, then you have an adapter with the gas.
Yeah, at the base, that's an aluminum machine piece.
But like the.
The shaft itself is carbon fiber.
All right, one part that I think could give, we kind of design, or you thought you rethink whatever.
What do you say?
Well, the competition is with other policies that use heat and get that one. That part of the use.
Use carbon fiber for pedals?
No, I mean,
3D printed pedals?
Yeah.
I can't say I've seen an entire pedal that's been 3D printed. I don't know many teams who use carbon 3D printing for some of their systems, but I have yet to see personally a team that has a 3D printed pedal, whether it be out of plastics or carbon.
There's two ways it can go.
Yes.
Either use more high design because it doing something new, novel,
Mhm.
or it breaks and you have to grab something out of the field or spot.
Correct.
So that's the two options basically with. You do it in a thing, having a very good sound handling of the map and the game need necessary.
Okay, yeah, that's what I need to figure out is the properties of the ABS, but the testing done on the carbon was done last year by Ryan for the steering column.
All ABS is under. Right? So basically, it will change somewhat if we put it to the committee. So make sure that you know all those things.
Yes.
And the final thing about 3D printing, what you're presenting here, if I understand it well, you have, it's a three-part piece, right? You have the
base,
you have
shaft,
the
pedal,
yeah,
correct.
base, shaft, and the pedal itself. Well, if you're gonna use 3D printing, why don't you use 3D printing to 3D print the whole thing?
Okay.
Right, because that's the advantage that you have with 3D printing. So you have one piece, if you design it well, you take a lower risk than facing failures where you're actually putting parts together. So reduction of the number of parts. And it will have some reduction in weight. You may have to reinforce at the right place, but I would strongly suggest that you actually consider making if you're gonna use any 3D printing, research your material, research the technology, and just 3D print the whole thing.
Okay. Yeah. The one thing about doing this is like the ability to use carbon for the pedal and a different plastic for a different material. I'm just saying for the cost perspective. But
Yeah, so can you give us an idea of what the cost right now, based on this, what the cost of the pedal is going to be?
I don't know off the top of the head. I forget what the hourly rate is for, at least for LSU's carbon 3D printer per volume, but
And put that in perspective to the cost of the entire car,
yeah.
because you may be saving a few dollars here, right? But how important are those few dollars that you're trying to save versus the possible positive outcomes of using maybe a little bit more expensive technology that will give you better fidelity?
Okay.
So these are the things that you need to weigh.
All right. We'll do.
You're changing the size of the rotors. Can you explain what some of the shortcomings were of last year's design and why you're changing your different caliber, your different rotor sizes, right? What you are now?
So last year during testing, well, I'd say the biggest thing probably besides the size of the rear master cylinder was the setting of the bias bar. I was just blindly following what we had done in years past about how we set the bias bar. And in years past, we just had the bias bar completely flat horizontal with changing how much the master cylinder threads into the master cylinder is threaded evenly. And during braking, you could see that or if you pressing the pedal, you could see the height or the angle of your bias bar change. And that's not how you're supposed to set it. You're supposed to set it beforehand. There's supposed to be a difference, an angle in your master cylinders because one will compress more than the other based off the difference in pressure between the master cylinders. So we had never properly set our maps or our bias bar. And so I think that's part of the reason why we had such a front, like a forward bias, and we never ended up blocking the rears, which is what we had a hard time doing, which is why last year, during testing, we found an old master cylinder that was a smaller diameter and swapped it in. So for this year, we're going to properly align the bias bar, and I went with a smaller master cylinder so that in case of, for some reason, we have a larger front bias based off of aero or some other factor, that'd be easily adjustable to set it more rearward and not have to change out a master cylinder. And then the rotor sizing was just also to help with the bias, like using the forces that go through your rotors for the torque during the transfer. And it was also to help with packaging to make sure that caliper, because going with a different caliper, your clearances are a little bit different from the old style, but they gave us, I think it was like a 1/4 inch of clearance between the wheel. We had issues with calipers clearancing themselves last year. There's a little difference between the models in real life. That was slightly the issue, but we just gave ourselves more clearance than what we believe might be different than the real life model. So.
I have a question. Do you have models of this caliper?
Yes, I do have models for it. Sorry.
Was that from manufacturer? You don't.
That was from a manufacturer, correct? It's on
And then the other question is, if I saw it correctly, so this one will actually bolt through the caliper into the hub? Or upright, sorry?
Yeah, it bolts into the, instead of like having the 2 ear tabs
Yeah.
where it mounts, it'll bolt directly to the upright.
So that means the upright will be threaded.
Correct.
So does that mean that's gonna be another hole in the machine? It's another like critical alignment hole?
Are you talking about another process to do?
Yes.
Correct.
Okay, so just making sure you're accounting for that, and the fact that those holes actually have to be aligned well.
Oh, and not slightly.
So in manufacturing tolerances, I know in the hubs last year, there were angles and stuff that were a little off that were okay because of how we manufactured it. So just be aware that that's gonna be a critical thing, where in the past that's not been critical.
Okay, so, all right, I'll move that. Anything else?
Is there somewhere maybe later, this would be for example, said we would these all uprights?
Yes, yeah, no, I have an assembly. I just wanted to include the picture. You guys can see the mounting here.
Pretty excited about your design factor 1.3. Is that like an overall vehicle design factor y'all are aiming for? Or?
No, that was just a personal one, just because weird things can happen in the brake system. I mean, this is a 40-hour run life car, and I didn't want a factor safety less than 1, but 1.3 was what I was satisfied with. Something that was easily available for a thickness of sheet metal, because we get all of our tabs sponsored by Custom Metal Works. So it's just a sheet metal thickness that's easily available that was thicker than the previous used thickness. But that's just what happened to be the factor of safety. It differs from system to system. So.
I guess I see it, a lot of the stuff is weight saving is what y'all are going after.
Yeah.
So,
I mean,
you had an overall, I guess, system factor safety, kind of give everything down to a, same design factor, probably shave weight elsewhere.
Yeah. Okay. Thank you. Next.
Just a personal, especially since this has to do with rates. 1.3 sounds a little
Low. Okay.
That's what my gut tells me.
You're good. I do some cutouts in the tabs, but I'll change some of the design of the tabs and I'll look into it, see if we're going to save weight and not save weight. But
Should be research. I mean, it might be worth looking to other teams maybe, or what people in the industry do for, racing.
okay.
I don't know what a normal factor safety is. This isn't really an ASME
Yeah.
standard type of deal.
And fatigue should be an issue. Yeah, maybe I think 40-hour car is a little bit, it's more than that if you're going to put it
Cool.
through.
Testing.
But you have fatigue.
Yeah, sweet.
Because, I'm not a race car driver, but, the brakes get beaten up and, it's a repetitive loading.
Mhm.
And fatigue is an issue, so make sure that you have accounted for that.
All right, we'll do.
One last note on that, because I know we ran into it last year for the repetition design. Is that 1.3 with extreme high load case? Or is
That was the
1.3?
load case that is given in the rules.
Okay. So then you may want to consider, because I know you don't want to double up, you don't want an extreme load case and a 1.5 factor safety. But if it's a conservative load case at 1.3 stage, because I know in a panic you may be able to do 300 pounds on the brake pedal or something like that. So That's all, you have a cockpit model, you can put a scale on there.
Yeah.
And measure like maximum force that the driver's out. Easy check, use that as your maximum.
Can I ask you, you talked a lot about weight reduction was your big objective, talked a lot about strength, very important. How about the braking performance of the car?
So that changes a lot. Besides the brake system itself, it also it will change based off of aerodynamics of the car, allowable G's that the cars can handle based off the vertical dynamic load on the tires. In previous years, the car with in 17 we didn't have air on the car,
Right.
and I think during competition on average it was like 1 point, or the highest peak braking was 1.4 G or 1.6 Gs, and the average was 1.2. And then in this previous year with aerodynamics, I think the peak was 1.8 with an average of 1.5. So, I mean, you want to design for being able to brake later so you can stay at a higher speed for an average, have a higher average speed during the course. But the efficiency of the braking system is up to the driver, when they want to brake versus how they feel they can handle the car through a turn. So, I don't know how to thoroughly explain your answer because I guess it.
No, I think you were getting at it. You explained previously without the aero, you've got some level of G, at the aero, you've got some new level of G.
Mm-hmm.
I guess what I'm getting at is with your new optimized system, are you able to step that up again?
I believe so. It also depends on the aerodynamics connection of the car. Last year, I think it was around 180, 200 pounds of downforce on that vehicle, and we're expecting upwards of 400. So it's more of the tire's ability to handle it now with the new package. So once testing comes around, we're going to be testing for it, but based off of the calculations we've done so far, it is higher. All right.
Thank you.
All right. Let's get moving. All right. We have Alyssa. I'll go with you. Okay.
All right, so Melissa did the frame this year. Our main goals for the frame were to weigh less than 60 pounds, which we ended up hitting a goal. We hit right at 59.5 pounds through SolidWorks evaluations. And then our stiffness goal was to be above 188 meters per degree, and we can talk about that later. And then also I wanted to evaluate an implementation of a carbon fiber structure combined with our steel chassis tubing. So some of the design changes were to have a thinner square tubing where possible, and also change the rear configuration of the car a little bit to save some weight. So I did a little experiment on the carbon fiber structure. We have our old 2015 frame, which is kind of out of commission right now. There's not much on it besides just the actual frame itself. So what we did was we went ahead and cut out the top bar where that foam piece is. There was a bar right there. We cut that out and we put in a carbon fiber section, and then we did a torsional stiffness test with the bar, without the bar, and then with the carbon. And as you can see, the results at the bottom, we cutting the tube out, we lost about 22% of our stiffness out of the whole car. And then adding the carbon back in, we gained back a little bit, but we still lost 13%. At the time, we had seen that it was unviable to use this carbon fiber structure for this year's car without further evaluation that we don't really have time to do at this point.
How do you attach the carbon fiber to the existing steel structure?
So we cut out this foam piece, and then we wrapped carbon fiber around the tubes and the foam itself, and then cured it around the tubes.
So basically, it's integrated. It's not something that you're attaching afterwards. It's integrated with the frame.
Yes, sir, it would be integrated. That's why I wanted to do testing before I sent out a final frame order, just so that I could make those modifications for needed.
Was that overlap onto the existing frame at a critical length, or was it kind of a, hey, we have this much length, let's just wrap it all the way?
I'm not quite sure I understand the question.
I guess y'all, you said you wrapped the tube onto the existing frame bar, the carbon fiber. Was that length that you overwrapped onto the existing bar? Is that like a critical length that was designed, or just kind of using what was available?
Medea could probably answer that because he laid it up.
So what we did at the full, put it on the, set up the power tube with some steps. Yeah, and put the phone there and wrap the part of the around the bottom, the little thing on the bottom side. Wrap the part of the bottom.
It's more like a panel, not a
So there
cylindrical.
was no part
Okay.
to,
Okay.
No.
just the part, wrap it around.
I wasn't able to get an actual picture of that before we hauled off the frame, but yes, it was wrapped around the phone. Sorry.
Okay.
After some FEAs, we found the model that I designed to be 1,669 newton meters per degree, which was 13.5% stiffer than last year's car. So we're very happy that it is stiffer than last year's car, but we did decide to stick with this and not do any more iterations of the design due to wanting to keep the car lightweight still. We were a half pound under last year, because last year it was right at 60 pounds. So we wanted to keep it lightweight, and also at this time we deemed that being lightweight is slightly more important than hitting that 1,800 newtons per degree goal right now. I think that's all. Yes, that's all I have for the presentation. Any other questions?
What's the weight difference between your new frame and the previous one?
Last year's frame was right at 60 pounds through SolidWorks modeling,
And for the new version?
59.5.
So you gained half a pound out of 60, and you compromised, what, 150 newtons per degree stiffness? So basically, there you go. Have you looked at the trade-off?
Other way around.
Huh?
Other way around, we lost weight and got stiff.
Did you see that the goal for stiffness was 1,800?
The goal was 1,800, yes, sir.
Okay, so that was the goal, not the actual number.
Last year it was 1450.
Okay, yeah, I have that up there.
Yeah.
Okay, yeah, I got it. So you gained, went up by 30.5% stiffness, and you managed at the same time to lose, half pound up to 60.
I think Kyle was
Where do you get your torsional stiffness, chassis stiffness goal number from? Is that kinematics driven? Is that just, we want to be better than last year? At what point does it matter how stiff it is or how not stiff it is? It becomes whole car vehicle better.
So it's kind of a balance between the both. It is kinematically derived, but also I based it off of last year's goals. With last year's goals, we were way under that. We had the same goal for last year. We were way under that goal, and we were still able to perform just fine. We had no issues with anything. So I decided the same goal for this year.
Did you have issues with last year's original stiffness? Like, why not keep it at 1,400 or whatever it was last year?
I'm not sure if I can answer that. I wasn't too involved with the frame last
I
year.
think that's kind of what you were kind of.
I don't.
I'm sure I'm
I
gonna
mean,
ask the same question to the kinematics person.
Okay.
Don't worry.
I don't think there were any major issues. I just designed it to
Yeah.
be as stiff as I could while being under the weight goal.
Yeah, and maybe at some point you say, hey, 1,200 is good enough.
Yeah.
Let's shave even more weight off. So maybe, find your upper limit. You don't have to keep increasing every year.
Your experiment with the carbon fiber. Why do you think you didn't get more increase in torsional stiffness?
Yeah. I'm not 100% sure. What I can,
Let me ask that in a more better way. What do you think you could do differently that would get you more stiffness with carbon fiber? That's better.
I would probably still implement a tube, but maybe make it a lot thinner, and also maybe do more layers of carbon fiber. At the time, I think we did two layers of carbon fiber, and it's over a pretty large surface area. So of course, there's deemed to be a good bit of like twisting.
Yes.
with that, but we decided to just kind of work with the frame that we had because we didn't want to chop up a brand new, well, not a brand new, but like a working car frame. And this was our only frame that we had available. So we did the testing with it.
Did you do any strength calculations before you decided how many layers? And,
No, sir, we did not.
yeah, so on the next try, I would recommend that you start by making some calculations. You can consult Dr. Palardi, who is in the composites area, the guy. Now, I understand this was something on the fly. Let's try and see if we get lucky. But I guess luck is not in the engineering vocabulary. It's in the real vocabulary, but not in engineering. Specifications, holiday specifications, luck, not there.
So I just wanted to say that I think it's awesome that you'll do the test. I think it's good that it's a quick and easy test to see if it's viable for this year, currently based off of the team. I do think that even though initial test says it's not better, I think long term, once you develop it, it definitely could be like really, really good. And y'all should definitely keep working on this and maybe even like senior design next year or something like that. It could be, I haven't seen any other teams do it, but just off my gut feeling, I think it could prove that to make like a really easy to make hand stiff.
You only did it on one side also, right?
Yes, sir. We only did it on one side, and we performed the test with the tube in, like as is, and we performed the test without the tube in, like that, and we just took an average of that side.
And maybe if this is something that y'all do want to move to, it kind of looks like you're slowly working your way towards monocoque zone. There's a lot of information and design research into monocoque design, even in FSA, and you know, a lot of times with different honeycombs or other materials in there. Maybe look at some of the other designs, like I was saying, ballpark some numbers where you think you'll be, and test it off of that basis. But there is a lot of research, a lot of monocoques in FSA already, so you don't have to just start from nothing. You can build off their one.
I think our biggest thing for this year was just time, not having the time.
I think perhaps get a start from the analysis you did, the FDA analysis you did, results. I'm sure you were naturally very high stress areas to figure out reinforcing doors.
At this time, we're not thinking about reinforcing them anymore because the highest stress concentration is at the top of the main voltage, and it just our front voltage.
No, I know you kind of met the goals that you want to meet, so you rose that up just as a point in the future. I guess if you want to develop it some more, I think you've got some information there
Yes.
that let you develop your ideas and maybe develop carbon fiber ideas more based on this type of analysis.
And just like a comment reminder from last year's design presentation. So make sure when you go to test this year's frame after you make it, we are going to test. One of the design judges has suggested instead of just measuring it at like one point, measuring your twist of the chassis along the chassis, so you can identify where the weakest spot is, which I think we kind of know where it is, but to have numbers to back it up would be really awesome. So just remember to do that.
And
Quick note, looking at your IPA, there's some stuff that's all of the front tubes need to be trusses so that you get an accurate rotation. Because you're currently getting bending in those tubes that you put on the front, which leads to a different result than you can compare to last. Should still be way stiffer, but it's not a great comparison because it's set up different.
Well, I performed the same FDA structure test on last year's spring as well.
Okay.
I did like side by side, same
Got it.
same constraints.
and to go into capstone interrogation mode, or when you're showing results, say express analysis, put the lobes out there and where they're located. Basically, put the loading scenario and the boundary conditions that you use for the simulation. Otherwise, it doesn't tell us very much. And little larger fonts, so we can, I guess, I'm an old man, and even with my glasses, just for a presentation standpoint.
Hi, everyone. My name is Van. I worked on the suspension components for this year. So the goals for this year was to lose 1 pound with a high goal of 1.6 pounds. And for our compliances, we determined goals of 0.3 degrees of hamper compliance and 0.03 degrees of max toe compliance. These were comparable from last year, just about, I'd say about 15% a decrease from last year's compliance numbers. And then for design changes, we want to explore a custom three-lug wheel center, reducing the mass of the uprights, both front and rear, and integrating wheel speed sensor mounts for the uprights. So here is a comparison between the 2018 and 2019 front uprights. I know it's a little hard to see based on the lighting projector. After running the FAAs, I did identical loading conditions for the bearing loads. These bearing loads were pulled off of 2018's bearing load calculator from what a previous team member had used. Oh, right. What?
Right? Yeah.
They're really a method of comparison. Yeah. As you can see, the factory safety for 2018 was around 1.17, and for 2019, 1.19. Comparably very similar. The calculations that were used for the bearing loads here were based off of different load scenarios. The two in here are based off of the autocross worst case scenario, where I pulled acceleration and G-forces from autocross and then compiled them together in longitudinal, lateral, and bump loading. So this is the peak loading you would see in any scenario during autocross. In addition to that, I also have load cases for purely longitudinal, purely lateral, purely bump to explore just singular unidirectional load cases for the most extreme scenario. After doing the main change with the 2019 uprights was the cutouts, mainly just exploring weight loss and weight savings. So with that, we saw about half a pound of loss from the uprights in total. That's front and rear included. So around for all four corners, half a pound loss. Using, like I said earlier, we're using data from 2018 comp in Lincoln, taking data from our data collection for the acceleration forces from 2018 Lincoln competition, and then applying 2019 expected loads. Some of the main changes were, the main change was aerodynamics, since we're expecting, instead of last year, they calculated expected aerodynamic downforce to be about 400 pounds. This year, we're expecting around 600. So that was accounted for as well in the loading case, loading scenarios. And then currently, I'm investigating fatigue failure. The factory safety numbers you see here are fatigue failure factory safety, not yield. So these are much lower than what you would see in yield factory safety. For yield factory safety, they were upwards of 2. 2 factor safety, which I deem pretty acceptable. But as of right now, for fatigue failure, I'm going to have to go back and revisit some of the designs and how I cut out the weight in order to raise that factory safety line. And I'll also have to explore more into the 2018 model and verify that those loads are valid to make sure that these factory safety numbers aren't just way off the ballpark. And then in addition to the front, these are the rears, which experienced about a 1 factor safety, which is definitely not where we want to be at. So again, I'd have to go back and revisit some of these load calculations in the calculator to verify if this is correct. But this gives me a pretty good ballpark of the changes of stress flow between both designs from 2018 to 2019. For the custom wheel centers this year, the step-by-step process is we used Altair's Inspire solid thinking software. I loaded a wheel center template with the basic dimensions of the lug studs and the mounting bolts to the rim itself. Ran a topology optimization for considering maximum stiffness, and then using 30% of the design space volume. After running that, and the loads that were applied were, I constrained the lug nuts or the lug bolt bores, and then applied a torque on the wheel centers. That torque was derived from a basic hand calculation of the forces seen from braking, since that is the most force that we'll see for these wheel centers in terms of rotational torque. And then after pulling that model from Altair Inspire, that was then generated in SolidWorks, in which I performed 2 different kinds of load cases, braking and cornering loads. So braking, like I explained earlier, was just a fixed center and applying a torque on the wheel rim mounting bolts. And then the cornering load cases was taking it was basically a weight or a load transfer derivation, taking the maximum or the weight of the car and its approximated amount of G's in cornering, which we approximated to be 2 G's, and then applying it to 1 corner. And then the load applied on the wheel center was basically kind of a bending in plane. So taking one third, and in this case, it was 1/3 of the wheel center and applying it in axis force. FEAs from that show of 2.4 versus 2.5, comparing it to last year's. Both I loaded both the generated custom wheel centers and then the Kaizers that we used in 2018, and then compared them. In comparison, the factor of safety of the custom wheel centers for 2019 are slightly higher, but ended up the same ballpark while losing 0.9 pounds, or not losing 0.9 pounds. They weigh 0.9 pounds versus 1.1 pounds from 2018. Yeah. Are there any questions? Dr. Strobel?
Science looks great. However, have you ever thought about how much extra machine time you have to invest for the minuscule weight savings that you?
Yes. So I actually just this week talked to Nick from the machine shop, asking him what his advice was on machining these uprights. He said that the setup time should be minimal because the orientation necessary to make those cutouts are all in plane. So it should take 1 setup to make all the cutouts necessary. In order to manufacture or to make cuts for the caliper mounting and getting the profiles right, that should already be part of the setup. So there shouldn't be too much extra time to CNCing the uprights. I also have 2, that's also my backup plan, because right now, how the uprights are designed, they're not in plane. I should back up. I have 2 versions of the uprights. One have in-plane cutouts and one have cutouts that are more, I guess, perpendicular to the surface of it. Right now I'm working with Branson on getting a 5-axis mill company or a company with a 5-axis mill to sponsor us to perform those cutouts. So in the case that doesn't happen, then we have another version of the uprights to fall back on. And manufacturing that should not be a problem.
My concern is just that you're getting minimal weight gains for a large amount of extra.
Well, we can definitely consider that. I'll make sure to double check with Nick as well as Jason from the machine shop to estimate the tool path and runtime for the CNC operation, to see how much longer that would take by going with the new design.
Two little notes, the little shafts you have that like connect them, that would all be like 3D machining because of like how they're oriented, and a little consideration may cut down a lot of machine time on that, but just how you model it, and like what tool you can use and stuff like that. Just like consider that, talk to Nick about it. Kind of there's some like some simple changes you can make to save a lot of machine time. That was one thing. Also recognize that, like, as you were saying, but again, you can almost think this is a multi-year investment. Once you do wheels once, you can reuse the wheels 3, 4, 5 years in the future. So something like that, maybe at least factor that into your consideration about machine time, as well as the weight savings, because you're going to pretty low. So you're also losing a lot of stuff like that. Right? So yeah, that's pretty cool. Another question I have, when you do your braking FEA, because your wheel center is not in the center of the contact patch of the wheel, you're also going to get some like some original effects, also like with your rotational force. So I mean, I see your factor safety is a lot higher, but make sure that there's not some weird. Try to think of every load case, because yours you may be making it stronger in all the ways you can think of, but there may be some weird load that yours is a lot weaker. So just, I'm always wary of wheels, but I think
I'll definitely count for that in a worst case scenario.
So that was something I wanted to bring up. I don't know how often it may happen, but in my mind, it's not out of the question. Is basically you lock the brakes and your wheels are turning, and then you're taking a tremendous load, which is not exactly intuitive if you assume that you're braking while you're straight and you're not. So have you factored that in, because it's a completely different type of loading than call it normal brake.
Yeah.
Did you take that into account?
No, I did not. I didn't take that into account, and so with Kevin's suggestion, I'll revisit the design and factor in the possibility of multiple forces in a braking event.
I have a couple of more questions on your upright. Sorry, you want to say something on this?
I was just saying, most of us as drivers, like, are you talking about braking while turning?
Yeah, right.
Our peak braking will not be in turning, because I know our tires will be able to handle braking while turning. So all of our braking, as most of us drivers do, we brake before we turn. So before you see a load of your peak braking while you're turning, I just don't think it's possible as the tires.
Depend on a human decision.
I think the tires would handle it, is what I'm saying too.
To check that.
Yeah.
You're saying that the tires will give before the structure will give. Is that what you're saying?
Yeah, the grip of the tires, like while turning, I think at peak we pull like 2 G's in turning, but there's the capability of the tires to handle 2 G's of braking and turning is something that we've never done in the car before. I'm not saying it's not possible.
Right, but right now that's kind of up in the air. So, and as far as I'm concerned, nothing is impossible until it's proven. And even if it's proven, sometimes things happen that you cannot imagine. But can you go back to your uprights? So did you use the same optimization software to decide where to remove material, or did you do it yourself intuitively by looking at the stress distribution?
Yeah, it was strictly based off of the stress concentration areas of 2018 and finding areas where there was low stress, and then making cutouts, testing the stress there, ensuring that the corners created from those cutouts don't cause any excessive stress concentration or stress razors.
And I assume that in your model, you had all corners, concave corners blunted by radii, and then you're going to give this to be manufactured. You're going to make sure that you have no sharp concave corners, no stress concentration.
Right. Yeah, definitely. I've gone through the upright design with Nick, looking at the different areas, and at some points you can't put a radio on everything based on how the CNC milling process happens, such as internal cuts where you can't get a bit in there.
Well, that's where I think what Dr. Sherman was saying in brief is designed for manufacturing.
Right.
Which, by the way, the cool design that you obtain by optimization for your brake, your
The wheel center.
right? The software does not account for manufacturing considerations.
Right.
And if you go a second pass, you will find that you may be able to make it much easier to manufacture if you consider that based on the shape that I saw, I would immediately think of water jet cutting to do most of the work. And then if you modify your support webs or structures, you may be able to minimize the amount of machining after you cut the pattern on water jet. So basically, what you need to circle back and do for all these parts is a design for manufacturing consideration, which, you know, so far has not been factored in formal.
Right. Yeah. So, like I said previously, I had talked to Nick a lot about the feasibility of designing these. One thing I should note on is that the geometry that you're seeing for this wheel center can all be done in a 2D fashion. The only 3D machining that might happen is that there's a slight concavity when coming into the center of the wheel center, but the small little spars or those sections, that can all be done in 2D. They're in a flat plane. So, but I'll take your suggestion.
So what I'm saying, there may be some optimization tweaks. This is just looking at it. It's obvious that you can do a major portion of this with a water jet.
Right. To get the main profile and then
to get a main profile.
Yeah.
But if you do a few tweaks, you may not compromise weight and strength, but make it cheaper and easier to machine. Also reduce the risk, because the more complexity you have, the more risk you have that you may be off.
Right. Okay. I'll consider that for revisiting the design.
Just one thing to note as well, if you are going to go to a 3-bolt pattern, make sure you remember you have to have 7 rain tires as well.
Yeah, so we have ordered, we placed a max industry order, or we're in the process of it, and we have nine blanks of these wheel centers for 2 sets, 1 spare.
And then, okay, so hopefully 1 spare is enough. The other thing is the tracks. While the track may be nice, the parking lot you're testing in sure isn't. So with some of your loads, potentially think about, you know, like they're saying, if you lock up your wheel, you're turning, well, your tire may not be able to handle it. You also drop off or hit a bump in the next section of pavement. And you're not just sliding on the bottom of the tire, you're ripping the sidewall off the bead. Maybe factor in some sort of worst case, unlikely, but definitely still possible. Exactly. You're not in the physics world, so don't plan as if you are.
Well, maybe like today, where we actually do the tile.
Yeah, like that. So, okay. That'd be a lot better if you rip the tire off the bead and then break the upper.
Yeah. I'll think about it for sure. John.
I just have like a little quick comment about the FPAs. So whenever you're like saying like we had a factor safety 2.4 on one and 2.5 on the other or whatever, just like on the upright, is that comparing the same loads on last year's versus this year's, or is this using the loads from last year's car and the loads from this year's?
They're identical loading conditions, so the same forces, the same constraints. And I'm also applying ISO clipping to ensure that there's no weird, super high, stress somewhere that there's not going to be. Yeah, do that.
Whenever you present design, make sure judge may say like, oh, you barely lost any weight, like that's not that impressive. But if you could say, yeah, I lost like 0.2 pounds out of each corner, But also because of aero, we had a 200% increase in load on these components. So like I lost weight, I have the same factor of safety, and our loads are way higher. And that's something to be proud of, and make sure you include that in the conversation, because they may not know that, that's part of the picture. So make
That's
sure
why the
you,
loads need to be up there.
yeah, present the load changes from year to year, as well as factor safety and what drove those load changes.
We're gonna take Kevin's as the last
Okay,
question.
last comment, I kind of got mentioned about what he said. Y'all are actually expecting almost double downforce that we made and running LC zeros. Your load base is a lot higher, for braking, for cornering, for all of that. Compared to ours.
I forgot to mention, we did approximate 150% for load cases, so all the bearing loads are times 150%, that counts for LCD.
Make sure to mention that.
Yeah, sorry.
Oh.
Okay, thank you.
I did kinematics steering. So a lot of what I did was kind of lap time simulation as a means of really providing a groundwork for kind of future work in this area and kind of competition-based metrics. So first one, wanted to use the simulation I had for 0.1 second of skid pad improvement, and kind of parameter involved there was the track width, the distance between the front two wheels. So that's kind of a compromise between inertia added with the extra width, load transfer on each tire, the weight of the entire car. Next one would be increasing the tire grip by 2%, which would be validated with the parameter in that simulation. So kind of across test data, kind of correlating that with the improvement, like the changes in damping, stiffness, kind of directly trying to relate that to improvement of the tire grip. Going back to the 1 second, so that number came about from, that would basically put us in the top ranks of skid pad ranking. So that was the motivation for that. And the same with tire grip. In that simulation is a scaling factor of the available grip, which would also contribute to that 1 second. And then with our new LC0 tires, basically they operate with demand for higher slip angles for the outside tires, for the more heavily loaded tires, meaning the outside tire of the car needs to steer more than the inside tire. And typically, for pushing it in the pits, you have the inside tire steering more to meet a common corner radius. So that's a compromise there. So results from this simulation were shortening the wheelbase by 2.5 inches. That is mainly driven by the huge sensitivity of the car's performance to weight, despite a little bit more sensitive and low transfer along the longitudinal direction. We could minimize that as much as possible. The track width in that simulation, there was basically not a significant difference in, not a significant improvement, with the concern of possibly increasing inertia and decreasing transit response. For testing purposes, we can add a rear anti-roll bar.
and reducing the acronyms I have. That is a compromise between going full parallel steering to give us the drivability at low speeds. So, skid pad lab sense is a simple overview of what's in MATLAB. And put the steady state simulation, so corner radius, how close you are to the inside cone, the weight, downforce, CG height, and it's an iterative calculation. It figures out the tire loads, interpolates from tire data, and you know how fast you're going, the radius, time it'll take you to navigate a circle. That's how that works. This is the results of that study, and the two parameters here, when you say 49% usage and 52% usage, that is a linear scaling of the max tire grip. So the simulation operates at peak tire grip. And as I stated before, like validating this through test data, that percentage is not a real number. I'm not sure how to say that, but it's just scaling the grip. We may be achieving that several different ways. But for example, skid pad at Lincoln last year, we had a time of 4.977. To get that result, I basically just changed that percent as scaling factor to achieve that, to achieve a time of close to that number. And then use that, use the scaling factor to kind of see how much we're actually using for the tire force. So 49 inches of front track, increasing the grip by this parameter that much give you 100 seconds. So if this is you see that inside tire here's a little bit less on the new car, outside wheel skills a little bit more. Kind of slip angle difference will turn the car in the wrong direction. Meaning that to complete this, the same corner radius of the outside wheel, you're short 5 degrees on the inside wheel. Meaning that the inside wheel is going to be pushing the car a little bit the wrong way. But low speeds, I don't think the car is power limited with our, and we would be able to, in this kind of issue, would come up with pushing in the track in the pits. But mainly just start this based off of improvements in the competition, pushing around. Questions?
On your track width optimization, I mean, it looks like it's just kind of maximizing. If your width increases, why not make it 100 inches wide?
Because the farther out those non-suspended masses are, that's yaw moment, which is required to rotate the car, and that's and when beginning a turn, the initiation of the acceleration of the mass, and that can slow it down. So you can quick beginning of the rotation as well as a quick steady state kind of just stability of the load. So it's a transient factor.
There are some other kind of study that I guess wanted to on the width. I mean, that makes it look like, hey, just keep going wider, your flat time just keep dropping. So I guess how do you optimize, your maximum width?
Right. So as far as transient studies goes, I'm looking into developing something like that. It is a lot more difficult, but in lieu of that, something that I also trying to do is just studying an actual inertia number resulting from different widths. And then kind of going across past performance, saying it would increase it by this amount, judging off of that. And without that knowledge of the added control arm length, the added steel brake lines, overall, with the amount of decrease resulting from that, it wasn't. It's worth it to make that change.
Might be nice just on this graph or on another graph, have it. There's only your two parameters, go on there should. I guess relate if that's something. Just say your optimal point is where these two lines cross, versus if you just look at this, like you're saying, it looks like you show it, but show on the same figure when you present it. Well, no, you're hurting yourself. You have too much yaw inertia. Then you can see where your two lines cross. Like this is half the data.
Yeah, especially since you know the reasons behind the additional constraint. What Kyle said is important that you show it. You show it in a quantitative manner. Because listening to you, I know that you know the reasons, limitations, put it up there.
Yeah, explain that you changed the element model.
Yes.
Can you just clarify what's the advantage they get from doing it?
The tires that we've switched to, compound, and the construction of the tire itself can generate more force, more cornering force when you have a higher slip angle. And some, with Ackerman steering, this would benefit you in high-speed cornering if the higher you load the outside tire, then you would need less slip angle. In the left, you wouldn't have to turn the outside steering much. So, but these tires, the higher you load the outside tire, which will always result in a cornering maneuver because of the weight transfer. It demands more slip angle to meet its cornering force capabilities.
So you're deliberately trying to generate more slip angle on the outside tire.
Correct.
That's clear. That wasn't clear to me before why you were doing it, but that explanation is quite clear. So, discussion about the presentation techniques. That's something I could do with your table. Show that by a diagram or something.
All right, we're gonna,
You've explained it there very well.
we're gonna take your questions.
Okay, it's kind of a long one, but so just walking through the kinematic process. We've talked a lot about a couple specific things, but what about overall car kinematics? Same roll stiffness questions. You mentioned the ARB in the back now. Where is your center of gravity? Longitudinal on the car. So walk through the whole kinematic. Did you start with the ride frequency and build off of that, or how did you design the car's kinematics?
So load transfer for lateral load transfer, track with inertial wheelbase and up with that you can roll gradient, but if you roll center heights. So not really having any significant looked at sensitivity as far as roll gradient sensitivity and changing the wheel rates, but didn't have any good metric to change our roll gradient by 1 or 2%, which is what we're looking at in the range of our springs availability. But kind of looking at, for example, the LC0 is operating at 12 degrees slip angle to get their peak grip in our load range, whereas our 25 speeds have 7 degrees. So looking at the time difference and making that a additional kind of turn of the wheel to get to that point. So in means of kind of compensating the transient behavior, looking at the roll centers. So I did some simulations in that. Wasn't able to find any highly sensitive areas in which numbers would change significantly by doing this. So just, and granted, like I didn't get too deep into the kind of actual kinematics, but camber, the caster, kind of anti-geometry, like that. This is mainly just looking at like any kind of low-hanging fruit, but couldn't make any decisions that would really make a difference. Couldn't find anything to prove that it would make that much of a difference.
Okay. I just say for the design presentation, have all that easily accessible because they're going to want to know what are your roll center heights, or how much higher is your rear than your front, and make sure you have something you can tell the judges. Say you have Claude as your design judge, you just tear apart everything you do regardless. But the more prepared you can be for that, the more information you can have ready to just put right in front of them, the better.
And that goes to, not just your presentation, but others. We need more schematics. And this is rather complex. And personally, I'm taken aback that you're able to, out of the top of your head or out of your mind, describe very clearly. But if you had a couple of the right schematics up there during your presentation, gave those explanations, you would, that way you not only avoid questions because you've answered them in advance, but you also amplify the good impression that you can make on the judges. So it's clear to me that you know what you're talking about, and that's number one prerequisite. And number two, almost equally important, is to show it in an easy way for the audience. And by the way, this goes for the other presentations as well. I would actually give preference to simple schematics that illustrate concepts in exchange for colorful FEA or fluid dynamics. You understand what I'm saying? This is basically for all of you. If anybody disagrees, I don't mind contradicting.
Well, I'm Sebastian. I'll be presenting on the aerodynamics, I guess, for this year's car. Mainly focusing on the front main wing right now, because same design is also working on some of the iterations of the aerodynamics. So I'm mainly in charge of the rear wing. But what the main design changes were for the rear wing was we were able to add another element at the top of our end plate, kind of above driver's head, with several hoops to feed a lot more cleaner air into it, no turbulence or dirty air coming in from the back of the driver's helmet or the intake and all that stuff. So that'll help us get a good bit of extra balance. We also are aiming for a goal around 150 pounds of downforce in the rear CFD result, which it's hard to correlate CFD with real life. You don't know exactly what your air is between them. I mean, you want to aim 110%, but with our results that we've had last year, and with plenty of potentiometers that are CFD, it's been a varying rate depending on who's CFD and what your parameters are. So we like to keep it around 150 pounds in our CFD result, and we're going to check it with real life. Also, the changes I raised the bottom of the main helmet up by 4 inches in the rear, which helps increase a lot more clean airflow to it. There's not so much turbulence coming around the driver's head or the, you see it, I don't have a picture of a car starting it, but the roll hoop kind of is like a triangular shape. So the further down you go, the more interference you're going to have in the airflow. So moving up 4 inches is going to help a lot with the air. And we also, like I said, added additional airflow. So here's like a basic geometry of our rear wing so far. We didn't have the final design, but pretty good estimate of what it's going to look like. A few changes are going to be going on, and we switched to a lot more aggressive airflow this year. Last year, they were designed for the first year team, and they did a good job being conservative in their aspects of manufacturing as well as efficiency of the airflow. And since we have a little bit more knowledge thanks to them now, manufacturing possibilities and other things like that, we decided to look into validating a more aggressive airflow choice, such as some of the ones you see here that have a pretty aggressive camber, and which will cause more drag probably, but which will cause more drag, but a significant amount. But from what we saw last year, we had difficulties with drag, and after our engine modifications, we were able to gain a lot more horsepower, and the problem of drag through the horsepower, or the horsepower loss through the drag, became pretty minimal. However, with a lot of air changes like this, we're going to be seeing a lot more drag exponentially. So we're going to have to keep in count the horsepower loss this year. And since we also have these high camber airflows at such high degrees of angle, you see a lot of like separation. Vortex shedding is the word we're looking for. So we see a lot of vortex shedding on the back of the airflow with high camber and high angle. And to help counteract this, I implemented a slat in front of the first element, which what it does is a really high angle, smaller airfoil. And the purpose of this is it helps re-energize the air flowing under the back of the wing, which really helps it connect the gondola all the way to the top of the drawing edge. And before running these results on these high camber wings, it's really difficult to have proper meshing and proper physics to have something actually converge with such a high angle attack. And in order to do that, it's pretty difficult to get accurate results. You have to really know what you're doing. And the slat helps. It helps the gondola pretty much converge. It makes it a lot easier for it to flow, and it's a lot easier for the CFD to pick up what's going on. So we go over next slide. And so these are some plots. Sorry, they're a little small. Here's a phase 8 simulation in 3D. It's just a 2D scalar scene cut out. But it's just a 3D simulation. Just 2D for visual thing. But it's simulated 60 miles per hour, and we have pretty good convergence here to get above the third magnitude. And this isn't a final design, so there's still some optimization going on here. But you can see the velocity under these air folds connected all the way up to the top. You do have some separation right there, but that has been corrected since then. So see a lot of a good velocity across the back of the airfoil, really high speed with a low speed on top. And we're making a lot more downforce because you have a higher coefficient lift. So anyway, so just this rear wing we're looking at so far in the CFD 3D model, we're looking at about 189 pounds downforce, which isn't like very useful. And just a simulation by itself, we have ran it in a full car simulation, sorry, and it made around about 130 just from the loss of clean air from the week. We feel like all the intake and the headrests and stuff like that. So just a starting point. I think it's good. I also learned that the top element failures are creating a lot of we're creating like a nozzle effect between the two layers of element, and it's actually feeding up the air on top of the wing, and actually with the messing with the difference in pressure on top of the wing is actually creating about a little bit less downforce than it would if you were to remove them right now. And so I'm still playing with that, but one way to correct that is by scooting the top element up further away so the weight on the bottom of the wing doesn't affect the air. So this weight doesn't affect the air and the pressure flowing over the top of you. And so I've been working with that and manipulating it to see how play a bigger role. Yeah, there's another graphic on the closer. If you all have any questions.
Is there a full width rear spoiler?
Is there? It's a 3 feet wide full inside side and inside side. And this model was ran with templates. It's just I took a scene down the middle.
So when you did your simulation on half the field, right?
This one was full field. Or
Yeah,
basically, or actually this one was half the field. Yes, it's
Right, you- the slats at the ends, right, to avoid the end effects. There are two slats, right?
Oh, those are inputs.
Right.
The inputs that we talked about.
Yeah, like terminology. If you go to the figure that you showed first.
Oh, okay. Okay, right, yeah.
Yeah,
This,
so is that half of the whole thing?
this is actually the full scale. I just deleted input. You can see the different airports. Maybe easier to do.
And you
The
did
slots
your
are the first element right here. And it's another one on the other.
wrong terminology on my part. And you did your simulation of the whole thing, or is it you cut it in half, take up that amount of symmetry?
In the simulation I'm showing, I did it. I took it in half.
So you use symmetry.
I have also ran it in full scale with the whole car model.
And so with regards to the results that you showed, what's your lift to drag or drag to lift ratio?
I didn't plot one. I should have. The drag on this simulation was about 1.2 CD, and I believe it was about 50 pounds of drag, and the coefficient of lift on here was 3.8. So.
Yeah, it would be good to look at that factor because it basically gives you one number, gives you a sense of what you might gain versus what you might lose. Right, and the other thing is make sure you have an image that shows the setup of the problem.
Right.
Basically, you have symmetry, boundary condition, you need to show that. What the inlet velocity is, what is the outlet boundary condition.
It's a velocity inlet with 60 miles per hour and a balanced pressure outlet.
Right, so basically one image, okay, appropriately labeled that with one glance tells somebody like me, here's how you set up the problem. So it would go a long way, I think.
I know I don't have that well images or enough information you feel.
And your numbers or your graphs are invisible.
Yes, sir, I know.
Therefore, it might as well not exist.
So feel free to make their own kind of overlays for those axes showing your important information.
Or download the data into use a graphics package where you can control the graph. I mean, these are cheap things.
Yes, sir.
Think of your audience.
What about the front wing?
The front wing is currently being done in the senior design. So I don't have too much control of that.
Well, so, but as a package, trimming it all out together, do you adjust, can you adjust any of your rear flaps or your flaps here to just balance out the car? What adjustability is there in aero versus accidentally making an undrivable car? You have two separate groups working on it, not much control over each other.
The two separate groups work on it, but I do work with them a lot. I'm with them pretty often in the CAD lab, sitting down, find stuff out. And the main, so like I said, we're still in like a heavy design phase right now. We're not anywhere close to being done. There's some results that we have for the rear wing, but the front wing is being optimized to feed the undertray and our cooling system better. And then I guess sort of from there, once that becomes optimized, depending on how it affects the rear wing, how it feeds to it, the rear wing should.
And then did y'all test with last year's aero package, any adjusting? Okay, is there any adjustment built in or planned to?
What do you mean by adjustment? Like in last year's package? Like,
And in last year's package, can you change any of the different, well, I guess it's really multi-element. It's a little more difficult than changing any of the different angles of attack, movements, or pressure of the car. Is there any adjustability in it, or is it just design it, do it?
yes. Well, in this year's car, in this year's car, I believe we plan to design our front and rear wing. And if we have a little bit off center pressure, we can change that with an alpha effect location with the undertray. Last year's car, we don't have too much. I mean, we didn't really do much to it. We used it to base up our real life testing data, or safety data, and just correlate to see what final error we get in there, how close it was, how accurate it was. So it was about, I think it was about 10% off of what we got in like. So and that's like full scale for each model. CFD, new CFD package to start. But there's not too much changing you do with the rear wing or the last year's car. Had a lot of turbulence going to it, into it from the rear wing, and a lot of separation off the back going into it. So there's a lot of drag. And one way to benefit that would be maybe to help it move it up.
What's the limiting factors? Does the front limit the rear or the rear limit the front?
Talking about in limiting factors of like how much downforce, like
Center pressure.
Yeah, it's like you want your center pressure to be not too crazy. So one of them you're going to be able to make more downforce than the other.
obviously based on our strength of our prime wing will be able to do a lot more. Or in theory, it was going to make a lot more downforce. So we I think we're going to constrain it, be a little more conservative on the front wing and not so aggressive in order to help feed the undertray, the undertray, as well as keep flow flowing through the car and feed our side arrow as well as our cooling.
Just historically, have y'all had a lot of downforce aero coming back in my day? I don't think there was very aggressive aero package with the car. There was none, right? Yeah, okay. So, so y'all are moving towards this. I mean, this is showing positive impact. Y'all know that this is the right direction y'all want to take based on the course layout and everything, or?
Yeah, the reason why it's such an aggressive aero package is because most of our time we see on the track is around 35 miles per hour on average. And so to get low speed or like with your Reynolds number at 35 miles per hour is pretty hard to get a high downforce number with such efficient low angles of attack wing. So That's why I'm aiming for more aggressive style to help increase our downforce at this lower speed. And so more designing around the 35 mile per hour mark and not so much of a 60 mile per hour grammar because downforce is so exponential that the difference between 35 miles per hour, 60 miles per hour is pretty crucial. Just trying to help us do.
Remember how heavy your car was back then? I wasn't actually on the team, but it was a heavy walker. So,
Yeah.
This will be our last question. I'd just like to see, especially if I was a design judge competition, I'm all for the arrow, strap a piece of plywood to it like a sprint car, obviously it helps. But as from a design perspective, I'd like to just see, an analysis of proving that the extra downforce, the extra normal load on the tires benefits more than the weight and elevated center of gravity of the wings.
Like
From a competition design perspective, if you can just show that clearly and say, look, this is our validation for why we do it, and then back that up with flat top.
So we're one more.
Start shooting at it.
Just throwing it out there, the Arrow was the highest scoring team for one of the last year comp. And I think the reason was because we had so you're showing one thing, but like when you actually present, you want to see all of the validation, have all of that data, have step by step, like how you did it. You'd be able to show all that, show everything you calibrated, everything, like be able to talk and explain all of that. Because there's a lot of stuff that, I don't know we don't have time. There's a lot of stuff that needs to back this up, and depending on who you get a very crucial arrow judge. But if you can prove at least what you did in your process, you can get a lot more points than just throwing a free CFD on there and saying how much you pay. Your process is very important for arrow.
I guess my lock in the depth zone is because we're still pretty heavy in the time phase, so we don't know which path we're exactly going to take it. So
That's fine, just forward on.
Yes.
Be ready.
Yeah. If you're gonna say you're designing for 35 miles an hour, show us some stuff at 35.
yeah, of course. I have both. I just wanted to talk about that. Thank you, Brent.
Okay, my name is Trey Pejan. I'll be presenting on the body this year. Okay, so for body this year, since there is supposed to be an under tray on the car this year, as well as some added aero package features, we want to try to integrate the body more into the design of aero a little bit. We also wanted to fix that. We had a small issue with the removal of the nose last year. There were little pegs that would mount the front wing to the front of the car, and it would make it difficult to remove the nose. So we wanted to try to design the nose to fix that. And a small goal, this is kind of a hard one to figure out. We wanted to just try to save weight where possible. I didn't really have like a specific number on that, but I can get more into the details of how we figure that out later. So the design changes for this year. The bottom of the nose is designed to help feed the under tray a little bit. And so that bottom surface is really dictated by what the aero team tells me that they need from the nose. The sides of the nose are also cut out to fit over the wing mounts. And then for the side panels, we're looking to remove a layer of carbon and leave it as a bare carbon for the paint scheme this year. So we lose a little bit of weight there. I'm going to go to the next slide. So this is kind of a general idea of like one of the experiments we've been doing with the nose. So you can kind of see underneath everything is all of the packaging requirements that the body has to be designed around. So in red, you see the placement of the front wing as well as the impact attenuator. Currently right now, this nose is actually too high and it produces too much lift. And so the aero team has decided that the front of that nose, very typically, probably needs to move down to maybe 2.5 to 3 inches lower than where it is right now. And so that's what we're going to do for that. And as you can see, also the sides of the nose were cut out, and there are small little slats to fit over the front wing mounting. So the entire nose, instead of having to like finagle it around those particular spots, you can just slide the entire nose off and then place it wherever you need to be, like inside the shop or trailer. And then we also designed it in mind with to be made out of 2-part mold. So we've been kind of doing the same thing for the last couple of years as far as manufacturing goes. Make one half of the nose, the other half of the nose, put the 2 molds together, and then lay up everything. But this year, what we're going to do is both of the halves have been molded separately. And so we're going to try to add some flanges to the molds to where the molds actually bolt together and you can make the nose one single piece rather than having to have two separate parts and then put them together with Bondo and whatever else. So I want to talk about the side panels real quick. This was kind of a strange design process. The elephant in the room was that we were going to be switching over to Dacron, and we talked a lot about Dacron, and there were a lot of good things about it and a lot of bad things about it. The main good thing about it was that that is the ultimate way to lose weight in the body, and there's a lot of teams who do actually do it. And from the numbers that I ran, just bare carbon, like a sheet of 3K carbon in comparison to Dacron, the Dacron is 50% lighter, and so that doesn't count any of the epoxies or paints that go on it. But the big problem with it is that once it's on the side of the car, it ain't ever coming off. And so we talked a lot about whether we really wanted to have removable side panels or try to save basically a half a pound out of both of the side panels. And we decided that we're going to go ahead and try to do a single sheet carbon fiber piece instead that can either be zip tied or bolted to the side of the car rather than using carbon. So the weight savings aren't going to be as significant. Hopefully we can maybe take about 20 to 30% of the weight out by doing this. So you move one layer of carbon, which is probably going to be the 16 layer. And so what we also talked about doing was to save time in the manufacturing process. The deadline to actually send our stuff out to our sponsors to machine these molds is kind of really quick. So we don't really have a whole lot of time to do all of the molds for every single part. So we're actually going to do moldless side panels this year, where we take basically a large flat sheet of aluminum. We lay up a flat sheet of carbon fiber on top of it. And then what we can do is water jet the shapes that we need out of that and then shape it to the side of the car however we need. So the whole idea is basically where all these gold lines are where there are cuts inside of the carbon. And each one of those panels would fit as close to the frame as possible. And you essentially tape those together so it has like a living hinge between each of the panels, kind of like how you see on the end of a book. So whenever you place the panels on the side of the car, you can form it to that shape, and then using only a couple of little points on the car, you can mount it and it'll stay in its own shape. So it's kind of like this sort of origami shaped side panel, but it still tucks itself to the side of the car as tight as possible, leaving the most room possible for side arrow to do whatever they need. And that's pretty much the summation of what body needs to do. There's not a whole lot with it. So I guess I could probably take a couple of questions.
How are you attaching all these panels to the frame?
We're going to be using, and like in my head right now, I'm thinking we're going to be using tabs. So the same thing we've kind of been doing over the last couple of years, but really, really small ones. So we'll probably like put a couple of bolts, maybe like I'm thinking one right here, one at the top right there, and then maybe like another one in the middle and another one at the top by the front roll hoop, and then a couple more for the front section of that.
So you mentioned not using Peterbilt to make the molds for the side panel. I'm a little curious on that. So a lot of carbon fibers strength for like side panels like this comes from geometry itself. Mm-hmm. So the bends in the carbon add strength when it's not a single flat sheet. Have you considered that by making a single flat sheet, you may need to attach it in more places, and therefore if you lose the weight savings from needing 4 more tabs? It seems like if you had like I just don't quite understand why you would not get the mold machine by Peterbilt when you could have a single layer that's strong and the whole piece just fits on the side of the car perfect.
Yeah, that was definitely something that I was kind of thinking about. Mostly that's just a deadline issue. It's the body, since it's kind of the one thing that sort of like needs to get last along with ergonomics. Those are kind of like the last 2 systems on the car that get finished. We're sort of in a bind for time. Like as far as I know, the deadline to actually have stuff sent to Peterbilt is this Saturday. And so there wasn't a whole lot of time to actually sit down and figure out.
You mean today?
Huh? No, next Saturday. Yeah, for the first week of November. No, not today. How many? Huge amount of trouble for other things. No. So for next Saturday, we're supposed to be turning these things in. And so for the body, it's a big waiting game on a lot of other different subsystems. So like the frame has to get finalized first. And so for me to actually start thinking about what I needed to do with the side panels, I'd have to see what the frame looks like, put it in Alias to surface it and everything. And the same thing goes with the nose and for the aero team. So it's mostly just a time constraint at this point. But it also saves time in manufacturing too.
I would just be a little weird, but I think that like,
Yeah.
I mean, yeah, the flat sheets will work, but I think that even just on aesthetic look, like tape hinges, it's not gonna look as good. Non-painted tape hinges are gonna look a lot worse than like a single big carbon thing. Just to,
Yeah. I'm gonna try
I
to.
mean, if it's not lightweight and everything, it seems, I'm not sure this. It's up to you to figure out what you have time for everything.
Yeah, I mean, it'll fall together the way that it needs to. I was honestly actually thinking about using the triangulation in the frame for like a design element graphically for the paint here. So it's also kind of intentional part of that.
So can you go to the nose part?
Yeah.
Apart from thumbing the nose too far up, is there a reason why the nose cannot be shaped more like what one sees in the real Formula One world?
Are you talking about like?
Because what I'm seeing there aerodynamically, granted, you said the nose is going to come down, but that passage between the airfoil, lower airfoil, is really not what I would expect from the aerodynamic standpoint.
Yeah, I can't really say too much as far as like how that actually affects everything. I'm not an expert in the aerodynamics of it. The only thing that I do know about it, and maybe one of the other guys on the aero team can kind of help elaborate on this. We have a couple of those guys in the room. But there was talk about whether to like raise it or lower it. And I personally was kind of concerned with the height of the nose being lower and then possibly running into the front wing and then choking airflow a little bit because of that. But they ran a calculation, or they ran a star CCM test with that particular nose shape. And they said that because it's so high that the front lift on it basically negates whatever the front wing is actually doing.
Oh, I understand. Yeah. I understand that part. So maybe one of the aero team can you don't have to answer now, but
yeah,
consider it.
Mm-hmm. I think for some of the cities, because of the voltage,
yeah.
So that's why they do that.
Yeah, trying to package it with like a decent curvature in between those two elements is actually a little bit trickier than most people would think.
Yeah, I understand there's a constraint of the impact absorber.
All right. Yeah. Anybody else?
I just wonder. I'm going to say straight up. I got the impression from your presentation that the bodywork's a little bit of a kind of just throw it on at the last minute because the last thing to do. I wonder if you're doing yourself a disservice there or missing an opportunity, because we talked a little bit about the aerodynamics around the front optimized. I just wonder if there are opportunities in there to do something to give you a little bit of a marginal benefit somewhere. Airflow or weight reduction or the stiffness increase.
Yeah.
I don't know what. I just think you're underselling yourself a bit.
Oh no, I definitely understand what you're talking about. We talked about some other strange things that we possibly do with body. Like there was actually talking about there's some teams what they'll do is on the front roll group they'll put this tiny little thing that looks like a small windshield, and that helps produce a little bit more downforce on the front end of the car. And so we thought about like, since there's this huge gap between the top of the front bulkhead and then the top of the nose as it sits right now, we're probably not going to be able to do this since the nose is going to get lowered. But we even talked about putting like a small air dam inside of the nose to do like the same thing. Yeah.
One thing that always fascinates me when I watch Formula One cars, I notice in front of the driver, they've got a little perspex type screen, and usually jagged. I can't think why, but somebody's obviously thought about it, done that for a good reason.
Yeah.
I guess it's to do with airflow, but there may be opportunities in there for you to get something, sell yourself.
Yeah. Possibly. I have to sit down and kind of look at things a little bit more, but.
Yeah. But I know you've got
it's a good question
as well. That's really like
Yeah.
One thing, just going back to kind of the size and the conversation between Dacron versus the multiple, like, take together panels versus a one-piece molded thing. Think about the weight of the tab, because I would be fairly confident that your tab count will be a way bigger factor in the weight than what material is made of. If you can use 0 tabs with Dacron, you may lose like 2 more pounds that you didn't even think about, because that's 10 bolts and 10 tabs, or 10 nuts and all that. And you're talking about maybe losing a quarter of a pound going from carbon to Dacron for the tabs. And it's also at times constrained. But as much as it's a racing competition, you need to get sponsors too, and aesthetics are important. So don't forget about that. Yeah. And then also going back to the frame testing, make sure those conversations aren't 2 separate systems. If you want to put carbon in the frame for like future years, it's also the bottom. You don't have to, it's the same, same boat.
Well, that was definitely something we talked about early on. Like if the decision was going to be to put carbon where that upper side impact tube was, then we were going to talk about like actually getting body to really sort of integrate into the shape of that. But I'm pretty sure we decided that we're not going to do carbon for that this year. So, all right, any other questions?
Y'all should test the original stiffness with and without the body, and consider if you want to use the body as load bearing. It's one way to go with it. Just saying.
My name is Wadia Soma, and I'll be going over ergonomics. The main goal was to weigh less than 8.7 pounds, which is the weight of last year. Also to improve insulation from rocks. The outside, we had an issue where the driver would always sit on rocks, and also major design changes. We're going to use less panels on the inside. The tub is going to have less carpet area, and not really a design change, but the layout process. I'd like to change that as well. So here there is a figure of the tub, and myself with the seat back. How I would solve the rocks from getting in that issue is by closing off the hole for the harness. That's where the rocks are coming in, where the harness hole is.
Be sure about
I'm 90% sure there's one up over the side. If the driver's laughing and they fall, I would go back.
So,
As the driver. We want proof.
okay, so, yeah, so the seat back doesn't close off the hole for the harness, and that's the problem I solved with you, where the seat back will close the rear half of the hole, and the front is just closed by the tub itself. And this is the model with the tub in the chassis, the current chassis, and this is a mannequin that I found on GraphTech. And let's shoot them. I also took anthropometric measurements of the potential drivers, who I thought would be drivers at competition, and applied them to the mannequin to make sure that our tallest potential driver, Sebastian, 76 feet tall, will fit in the car. And he actually, according to this model, he will. So his knees will be better. And also, I made sure that the template fits within this model. The layout process that I'd like to do is to use infusion type layout, and that's kind of complicated. But instead of having the white cloth that we use to absorb excess epoxy, we replace that with a mesh type ingot. And the advantage of this is you use less resin because you vacuum the part first, and then you let through the resin. And the resin is also cheaper. The initial cost of purchasing everything would be about 10% less than we would that what we purchased of all the carbon stuff pretty much last year. So it's not really a lot. We paid about $500, about $950 initially. So then $90 cheaper. But that's just the cost. But this process also uses less resin. So, and the resin itself is cheaper. Yeah, it's cheaper than per gallon. It's cheaper than version. So that's the advantage of with the cost factors added up should add up well. That's it for
Just one thing with vacuum infusion,
yes.
it's definitely worth getting some extra because when a part fails, the whole part has to be redone. There's
Absolutely.
not really much saving, but it is nice to see moving to that. It is much better process. You can get better conditions, stronger, lighter parts.
It also seems like, could be way easier and cleaner to do. too.
It's definitely cleaner because you can
You don't have to mess
control
with it.
you can control the you don't have to mess with it. You don't touch it. You also have exact control over the resin and the flow. So because you vacuum the part first before you let there's a this is a spiral tube. That's where it sucks to. And in the middle of the part you put a tube with the resin in it, and that's where it all that's all and also has a valve, so you can open it up as you wish. So then you vacuum your part, and then you open up. When it's all vacuumed, you open up the valve with resin and let it through. So then you can actually see I think you can see better on the screen. You can actually see the resin flow. So over here this is where the resin is, and it's flowing towards this way. So you can you have visual control over the resin, over where it goes. So you also use a lot less waste because you can stop the resin before it gets to the spiral tube.
Make sure that you'll I don't care what the parts are or whatever, but get this process started, start practicing. It's gonna be a new thing. Don't wait until.
So the only difference is that we use the consumables are different, but the molds will be the same process.
Yeah. But I'm just saying, there's gonna be a little bit.
Yeah, there's definitely gonna be a learning curve.
Maybe the resin doesn't get over at this corner, because the shape of the part and stuff like that.
And that's the thing too. So because the way you can design molds, you can have this spiral tube go around the edge of where. So if you have a mold like this, you're laying up inside of it, you can have your spiral tube go around the edge, have your resin be at the middle or wherever, or at multiple spots even, and then just flow. If this spot is taking too much resin, you can just close it off and have the other one open. Stuff like that. Yeah.
So the part basically right behind the seat, does it still basically come up behind the seat and
Yes.
go vertical down?
Yes, that's going to be the same thing.
Vertical part.
So this, I still need to change this area. There's going to be, it's going to be flat, and that's where the.
So it comes up, kind of the seat bottom, and then
Yes,
it goes
so
down.
you can kind of see over here.
Okay.
This line represents where it goes up.
Okay.
So it goes up to here, then goes to the.
I mean, well, my question is, does it go
Yeah, it will
back
go,
down?
yes, because that's where the structure comes from. That's where you're gonna sit on.
It's also your firewall for rules for your seatbelts.
Yes.
So that was the main thing, for rules, because you have to have that firewall there. And how we do it with the seat, at least last year, if it's a similar design, make sure you don't cut that out, because otherwise
Okay.
you won't have a seatbelt.
The rules haven't changed from last year. For this, the rules haven't changed much.
Yeah, exactly.
It's the same rules.
As you do, one thing to note, I know Bobby talked about time constraints as well. One thing to always be reminded of whenever you're moving towards it's more advanced, better systems, especially when it comes to composites, is you need to be on top of your game because the bowl design is so much more important, so much more critical that if you move more towards this vacuum infusion and ultimately pre-preg, you don't have time to, oh no, we messed it up, we need to do it in a week. You just need to be way out in front of it, make sure the bolts are designed with enough lead time that if you do have to change it, you have time. Yeah, just slaps it, or you can always wet lay it.
One last thing, real quick, I know we kind of said we don't think the rocks come through the seatbelt holes, but despite that, that is one area with the rule about the firewall where like nearly every year we put everything together and then throw something crappy on there, close out the hole. So you could actually design that and make it look nice. It would be
This fits. Last year we don't have the firewall pass. That's one of the good things about it. So as long as it's there, you're good. Maybe, yes.
there's a lot of things.
Now I'm one, not here to make it. Yes. This is a steering wheel. We like to have a stronger steering wheel base, and we revised the previous design, made some structural correction. The base plate was changed slightly, and the shifting paddles are being redesigned for the base. So this is last year's steering wheel, this year's steering wheel. This so the design changes on the plate itself are the people are on bottom are less for more structure, and we have the paddles have a bigger area so you can press it easier. Instead of using just one finger, your top finger, you can use 3 fingers and your bottom. But yeah, and I think we also decided to redesign the back half of the handle to have the bottom part go around. Yes. That's right. Yes, and this is well, this is not really accurate because we printed the paddles. So this mount was printed with ABS. Yes, with ABS. And during what was it, Lincoln? UTA. During UTA, our drivers had too much fun and they broke. This year we're gonna have a gusset over here. So at least that's what quantum to increase the stiffness and strength of the paddle. And also the major another change is that we need to have metal sleeves going through the plate to attach the bolts. Yes, that's.
Are you looking to why that failed? I mean, just for fatigue or?
Yes, from fatigue and the drivers are running way too long. Yes. Want to shift off over. But both of them actually broke. So it's probably I'm not sure why, but they definitely outlasted their life because they have the car has a 40-hour life cycle. They've been accident more than like 41. Yes, it's perfect, bro. Yeah, so they definitely outlasted their life cycle, which is good. And yeah.
Kind of tying back in with the brakes, I know we talked a lot about 3D printing there. Is that these are still planned to be 3D printed paddles, right?
Yes.
Just again with the FDA,
So
your properties aren't exactly.
Exactly. So that's what I meant. So it's not really accurate because that's not. It's just SolidWorks assumes that's stock,
right?
Not printed.
And then with that as well, I know we've had some debate or issue in the past as well. Are the plastics and resins used UV protected? Or is that an issue that contributes to the failure? The steering wheel spends a lot of time upside down on top of the car in the sun.
Right. That's good.
good suggestion.
Things to think about.
Talking about the 3D printing, I would definitely consider the soft carbon fiber. You know, because this year there's a printer available that wasn't before,
Yes,
and I can tell you in terms of strength,
yes.
basically same size. The one that came out with the soft carbon fiber and this Onyx proprietary polymer was almost unbreakable, you know,
Yes.
compared to the same sample printed on any of the other plastics. So that may give you an advantage right out there.
Oh, I will take that into consideration.
But that's, see, pants engineering, make sure you proper.
No, no, Indeed.
So they need to get the properties of the outcome and do the calculation, factor in the fatigue, and at the end of the day, it's a different material that is available.
Absolutely.
The seat of the pants is that should be absent under all circumstances.
And on the other hand, if one of your main sponsors suggests something, sometimes we're thinking happy.
Yeah, correct.
You don't have to make me happy, you just have to succeed.
Indeed. That's our goal. Any more questions? Yes. Thank you.
This is our last one.
So my name is Josh Phillips. I'm a company drivetrain. So this year we wanted to test the lock versus unlock differential to see if switching to a spool design would be better. And then we also wanted to minimize the weights of the diff mount. And so some design changes, we removed some excess weight in the differential mounts. We cut out some, we made some cutouts to find it. And then we relocated the chassis mounting points to make the measuring between the diff mounts easier and make sure the alignment was correct. So to test the lock versus unlock differential, we used a Drexler limited slip differential that has an adjustable ring on it to that can adjust the preload on the clutch plates. So where we can basically lock out the differential with a little crank and then unlock it immediately afterwards. So on a testing day, we did a test on skid pad where we just back-to-back testing to see which one's faster. And the unlock differential proved to be faster by a few tenths of a second, which is a measurable difference in skid pad. So by that testing, we decided to continue using the Drexler limited slip differential. So these are our diff mounts for this year. As you can see, there's lots of cutouts in these. So last year, all these were full. They were just really filled in with aluminum. And by using these cutouts and doing different FEAs, we were able to cut out about 11.2% of the weight, which is an ounce and 1.76 ounces. And so these mounting points are the ones we changed to make sure the alignment was correct. And so by making these identical on the car, you can measure the alignment better, basically from last year. That's all I got. So any questions?
Hinge or compression?
That
Did
is,
you do any sort of buckling analysis on it?
yes.
Compression.
Yes, we did buckling analysis, and basically these trusses in the middle were able to stand up.
And the bottom one is.
Yeah,
Okay.
this is on the right side, which barely standing loaded, so that's why it's pretty much open in the middle.
I definitely like the changing it, making it easier to measure distances, center. That's awesome. I really question if that is worth 1.7 ounces. Is it worth it to have that Swiss cheese on the car? I know you want to make it lighter. I know you want just question if it's worth it. If someone walks up and steps on the diff, like it's hanging out the back of the car, if someone walks up and steps on it, loads it the wrong way, is it gonna fail? Like, it's awesome. Definitely the measuring thing is awesome. I'm not sure that consider the holes. Is it worth, I mean, the driver cannot drink one glass of water and save more weight than your diff mounts. Like,
make sure you think about, is it worth it there? Because the last year's did not scare me. Those are terrifying. I don't want to don't limit innovation, make it better. But I'm not sure this is the 1.7 ounces you want to chase. That's just my opinion. I do like to make it easier.
It still has a factory safety of 4.
I know, yeah, that's over that.
But I went low.
So we use load calculations for the slipping of the clutch in first gear, which is the highest torque that the engine can produce on these diff mounts. So we use that, plus in the method alone, we add another 1.5% factor or 1.5 factor of safety. So using those calculations, plus the extra factor of safety that the FEA has produced, that's where the factor of safety of 4 can go.
What's the location most likely?
Most likely the fail location would be, so I can't really reach it there, but basically this area up there.
Sorry, cheap shot.
And you show the PowerPoint.
No, it's all right. Okay, cool.
So yeah, right in this area is where it's most likely to fail. But even there, it had a factor of safety of around 4.
So, the webbing that we cut a big old hole in is like, I don't know, 60 thousandths of an inch thick or something, right? A millimeter. 0.09. The reason why, so on the bottom diff mount on here, the big old ring on the outside is an 1/8 of an inch thick by like 1/4 inch thick, right? On this side of the ring, there's tons of extra weight there. The only reason that diameter is so big is so those 2 bolt holes will line up on other diff mounts, that X brace on it. You could totally cut out like way more than your 1.7 ounces on the back side of that strap instead of trying to cut out that pocket. So just think about where you're losing weight, because one person decided they were going to lose weight out of the middle of the different one here. You don't have to follow down that same path, because there may be something else fixed that back.
Just to continue, the whole part where it's thick on the outside of that bearing, that's just solid aluminum, right? And the part you cut out is 1 millimeter thick. So if you like step it in and hug the bearing a little bit, similar to the top one, the smaller bearing, I think you could easily lose more weight and still keep some sort of webbing in between. Or I feel like that would be a much safer bet, because I'm not worried about them failing in driving the car, I guess. Maybe. I mean, you get some weird impact loads, but like, I feel like you have nothing bracing at all. You can walk up and squeeze it, and I'm 90% sure they would flex like this. So, trust it. No.
Maybe make a spare with Buddy.
SPA, someone poking the side of you.
Is that the FEA first command, right there?
Yeah,
Like somebody step on it.
50 pounds. 100 pounds.
Yeah.
Do the hand.
Okay.
All right, so that's the end. I want to thank everyone for coming today, especially for such a long presentation. So we definitely got a lot of valuable feedback. At this time, we're going to try to do a quick little shop tour for anyone interested, and that's about it.